Hi everyone. This is our last of the 4 trig units. You've made it. Okay, this one's very important for next year as well. We're going to learn the graphs of the sine and cosine functions today, and also we're going to do transformations, so back full circle to the beginning of the year. So our learning goals are to learn to draw the parent functions of y equals sine x and y equals cos x, so 2 new parent functions, and then learning to draw the image functions of transformations of the functions y equals sine x and y equals cos x. So we have to figure out what does the parent function y equals sine x look like. And to help us with that, we're going to use the unit circle. So we're going to complete the table of values and sketch the sine function y equals sine x for the interval 0 to 360. So we know that from our unit circle that the sine of a value on the unit circle is its y value. So the sine of 0 degrees is 0 degrees. So this is my x value 0, and then the y is the sine of 0. The sine of 0 is 0, and 0 to 1 decimal place is still 0. So what I would be plotting, it would be an x value of 0 and a y value of 0. So the sine function starts at the point 0, 0, right there, okay? And then at 30 degrees, the y value is 1/2, which we also know as 0.5. So we know that when our x value is 30 degrees, our y value is 0.5. So we're going to plot the point 30 degrees, 0.5. Okay, and then 45 degrees, the y value is 1 over root 2. And probably you don't know what that is off the top of your head, or you might, but 1 divided by the square root of 2 is approximately 0.7. So when x is 45, and then look at our x-axis here, it's each square is worth 30, so 45 is going to be here like halfway between 30 and 60, because it's 45 is 15 more than 30, so it's going to be halfway. Our corresponding y value is 0.7, so 45, here's 0.5, this is 0.75, so 0.7 is about here. And then at 60 degrees, when our x is 60, the sine of 60 is root 3 over 2. So the sine of 60 is root 3 over 2. And root 3 over 2 is about, it's 0.866, so about 0.9 to 1 decimal place. So when the x value is 60, the sine of 60 is 0.9. So 60, here's 0.75. So 0.9 is about here. And then 90, the sine of 90, so the y value at 90 is 1. So 90 and 1. And then 120, sine of 120 is root 3 over 2, which we already figured out was 0.9 to 1 decimal place. So 120 and 0.9. Next one is 135 degrees. 135 degrees, the y value is 1 over root 2. Which we already figured out was about 0.7. And then 135 is 15 more than 120, so it's going to be the halfway point again. And 0.7 about here. 150, the sine of 150, or the y value is 1/2, which is 0.5. And then 180, the sine of 180 is 0. And then the next, oh sorry, 0, fill that in my chart. 210, the sine of 210, the y value is negative 1/2, or negative 0.5, so 210 and negative 0.5. 225, the y value is negative 1 over root 2, sine is negative 1 over root 2, which would be negative 0.7 to 1 decimal place. And that's going to be 15 degrees more 225 than 210. So about here. Sine of 240 is negative root 3 over 2. Or about negative 0.9. Sine of 270, y value is negative 1. Sine of 300, y value negative root 3 over 2. Negative root 3 over 2, which is negative 0.9. Sine of 315, y value negative 1 over root 2. So 315, 15 more than 300, about negative 0.7. Sine of 330, negative 1/2. Negative 1/2, and sine of 360, back to the start again, 0. Okay, and then we wanted, it's not a point to point, but it's a smooth curve. So we want a smooth curve, and I kind of think of this first part as a frown. There's my frown, smooth curve. And then the second part is like a smile. So I've got this frown going into a smile. So that's one cycle of the sine curve. So this is y equals sine x, the parent function. And it looks like this wave. They're often called sine waves as well, as you can see. So that's one cycle, because if we went to 390, which is 30 degrees more than 360, we'd be back at a half again, and we would keep going in this regular pattern every 360 degrees. So this is one cycle using wave language of the parent function y equals sine x. All right, so we're going to do the same thing and see what the parent function of y equals cos x looks like. Again, using our unit circle. So cosine on the unit circle is the x value. So we want, when x is 0, we want the cosine of 0. Cosine of 0 is 1, the x value. So the point 0 for x, 1 for y. This is going to be on our parent function for y equals, the parent function of y equals cos x. Cosine of 30 degrees, the x value, root 3 over 2, which we know from the previous question is about 0.9. So 30 and 0.9. 45, the x value is 1 over root 2, which we know is about 0.7. And 45 is going to be halfway between 30 and 60. 0.7 is about here. Cosine of 60 degrees is a half. Cosine of 90 degrees, sorry, x value at 90 degrees is 0. Cosine of 120 degrees. So 120 degrees, x value is negative a half. So 120 and negative a half. And then 135, the x value is negative 1 over root 2, which is negative 0.7. So 135 is going to be 15 more than 120, so halfway here. And then negative 0.7 is about here, because this is negative 0.75. And then 150, the cosine of 150 is negative root 3 over 2, which is negative 0.9 approximately. Cosine of 180, x value is negative 1. So 180 and negative 1. 210, cosine of 210 is negative root 3 over 2, or negative 0.9. Cosine of 225, x value, negative 1 over root 2, negative 0.7, so 225 is 15 more than 210. Cosine of 240 is negative a half. Cosine of 270 is 0, the x value. Cosine of 300 is positive a half. 300 and positive a half. 315, cosine is 1 over root 2, positive, about 0.7. 315 is going to be 15 more than 300. Cosine of 330, positive root 3 over 2, which is about 0.9. And then cosine of 360, back at the beginning again, cosine is the x value 1. And there we have then one cycle of the parent function for y equals cos, and we want to again join it with a smooth curve. So between 90 and 270, that's where your smiley face is. So just try to do like a smooth smile there. And then what happens between 0 and 90 is it's like half a frown. And then same thing between 270 and 360. It's half a frown again. So there's y equals cos x, the parent. And instead of like sine, looks more like what you traditionally think a water wave looks like, with the crest and the valley. And then y equals cos x looks more like, I guess, what you'd think of a standing wave looks like. Okay, so those are our parent functions for y equals sine x and y equals cos x. Okay, so there's lots of wave words that are kind of math words as well as physics words in math and physics. They kind of go together a bit for this sine and cosine curves. So because of the shape of their graphs, the sine and cosine curves are often called the sine and cosine waves. In physics, trig functions are used to model wave phenomena. 3 words that are used to describe waves are amplitude, period, and phase shift. So the amplitude of a sine or cosine curve is the vertical distance from the central axis to the maximum. So let's look at our picture of sine first. Sorry, make sure it's in the frame here. So here's the central axis. I'm going to draw it in red. So the central axis, if there's no vertical shift up or down, so for the parent, it's just the x-axis is the central axis. So the difference between the central axis and the maximum, you can see here. So here's the maximum. This is the maximum there. You can see this distance is 1, and that's our amplitude. So the amplitude, usually I use AMP for amplitude, is 1 for the sine curve. And then you can see for the cosine curve, the central axis is again the x-axis. Splits it in half here. And then again, you can see in 2 different spots here that the maximum value is 1. So the amplitude, the distance from the central axis to the maximum is 1. Amplitude's always positive. That's an important thing to know. Amplitude's always positive. It's considered a distance. It's always a distance from the central axis to the maximum. So the amplitude of a sine or cosine curve is the vertical distance from the central axis to the maximum. So if there's no vertical stretch or compression, if it's just the parent sine or cosine curve, the amplitude is 1. Okay. The period of a trig equation is the distance along the x-axis that it takes for one complete cycle. So distance along the x-axis it takes for one complete cycle. And here it says that the sine and cosine functions are called periodic functions because they repeat every 360. So remember, period is the distance along the x-axis for one complete cycle. So we just learned, like, for one complete cycle of the sine curve, we start at 0, and along the x-axis we stop at 360 before we would start repeating again, okay, before it would do another cycle. So the period is in degrees, 360 degrees for one complete cycle. And the same thing for the cosine function. So for one cycle we start at 0 on the x-axis, draw all the way until 360 along the x-axis, and that gives us one complete cycle, starting at 1, going down to 0, down to -1, back up to 0, and finishing off at 1 again before we would start another standing wave. So again, the period for the plane cosine function is 360 degrees. Okay, and the phase shift of a trig function is the distance left or right from the normal sine or cosine curve. So for our normal sine and cosine curves, they're starting where they're supposed to start. So if the parent for sine is supposed to start at 0, 0, and the parent cosine function is supposed to start at 0, 1, so they're not shifted left or right. That will happen when we start doing transformations. So these current parents have no phase shift. You would say their phase shift was 0 if they asked you. And it was degrees as well, because it's shifting left or right. You'd be shifting on the x-axis left or right, and the x-axis is measured in degrees. Sorry, guys. And the y-axis is just measured in regular numbers, regular values. And phase shift, it's got the same meaning as horizontal shift, left or right, does in regular transformation talk. It just has a special name, phase shift, when we're talking about sine and cosine curves, because we want that word phase shift to mean the same thing in math as it does in physics. Okay, but for you guys and for this year, it's like the horizontal shift. And the term vertical displacement is used for vertical shifts. So instead of calling it a vertical shift, the wave word is vertical displacement. Okay, and then also it's important to know that the vertical displacement is going to end up being the new location of your central axis. Okay, so that's important. That's an important thing to know as well. So The graphs of y equals sine x, so the parent, and can be transformed to y equals a sine b x minus h plus k. So this is very similar to the other functions, parent functions that we learned how to transform this year. So we learned how to do the square root function, we learned how to do the absolute value function, and we learned how to do the reciprocal function or the hyperbola. And then we already knew the parabola and the line. So now we're adding two more, and they are the sine and cosine parents. Okay, but the transformations are going to work the same. And some of you might be a bit rusty on them, and we'll go over them all again as we do this. Okay, so the graph of y equals sine x can be transformed to y equals a sine b x minus h plus k by applying what we know about transformations to the parent function. To draw the parent functions y equals sine x and y equals cos x, we're going to use the 5 important point method with maximums, minimums, and zeros. Remember, zeros are the same as x-intercepts. Rather than writing out all of these points. Okay, we don't want all these points. We want these specific points. So this is an important point, our 5 important points, where our maximum is, so where we start, where our maximum is, another x-intercept where we hit the axis again, where our minimum is, and then back where we finish our first cycle on the x-axis. So for sine, those would be our 5 important points, which would be 0, 0, 90, 1, 180, 0 again, 270, -1, and 360, 0. For cos, these are going to be our 5 important points. So where we start at 0, 1, first x-intercept at 90, 0, our minimum at 180, -1, back to the x-axis at 270 and 0, and then back to our maximum at 360 and 1. So 0, 1, 90, 0, 180, -1, 270, 0, and 361. And they correspond to our unit circle as being this part of our unit circle. So the t, or the xy axis, so we're looking at that point, that point, that point, that point, and then back to this one again. So those are our 5 important points. And for sine, it's the y values. And for cos, it's the x values. Okay, so those are our 5 important points. And really what you remember, like when I learned this, was that sine starts at 0, 0, and then it does this. Okay, and then cos starts at 1, 0, and does this. Okay, or sorry, starts at 0, 1, and does this. So this is the x-axis and the y-axis. So we've got our kind of familiar water wave and our kind of standing water wave. I want to think about them like that. Okay, so now we're going to go right into transformations. So our first question, sketch the graph of 2 complete cycles of each trig function. State the amplitude, period, and phase shift of each. State the domain and range. And note that in this unit on trig graphs, we only state the domain for the cycles that we draw. Okay, whatever they ask you to draw, that's what you're going to state the domain for. You're not going to say that it goes on forever in both directions. Okay, that's just kind of like a quirk of this, really, but you only state the domain for what you actually drew, and they usually will give you a number of cycles to draw or draw what fits into a certain part of your x-axis. All right, so if you're given a question like this, the very first thing that you're going to do is label your axes. Okay, so you have to scale your axes. You've got your x-axis and your y-axis. So for the x-axis, every square is going to be worth 30 degrees, but I don't want to jumble it all up writing in all these angles here. So if we know that each square is worth 30, what we're going to do is every third square is going to be 90. So this goes starting at 0, 30, I'm not writing it in though, 60, 90, and then 3 more. So this would be 120, 150, 180. And then 90 more than that is 270. And then 90 more than that is 360. And we have to do 2 cycles, so we keep going. 90 more than that. So 360 plus 90 is 450. 90 more than that. 450 plus 90 is 540. And then 90 more than that is 630. We can also go in the negative direction, so 3 squares in the negative direction is negative 90 degrees, and then 3 more is negative 180 degrees. So first thing you're going to do is scale your x-axis. So make sure that you do every third square is 90, okay, which gives you a scale of 1 square is 30 degrees. Make sure you have degrees listed, okay, with your x-axis, and now you've done the x-axis. For the y-axis, we're going to do every square is worth 0.5, so every 2 squares is 1, just to spread it out a bit so it looks better when we sketch it. That's our reason for doing that, okay? Rather than having 1 be right here, it makes it too kind of tricky to draw. And then this is going to be -1 then, -1, and then -2. So first step, draw the scale. Second step is to draw 1 cycle of the parent. And I'm going to use the strategy again of drawing the parent in kind of our permanent color, pencil crayon, and then do our new one with transformations in pencil so that if we make a mistake, we can erase it easily. So we're going to draw our parent function for sine. So my parent function for sine is just plain y equals sine of x. And I know it's 5 important points, so it starts at 0, 0. Then at 90, it's up at 1. 180 back at 0. 270 down at -1. 360 back at 0. And then I'm going to draw it in. So this is a frown. Try to make a smooth frown into a smooth smile. Okay? And then now we're going to start doing our 2 cycles of our image function. So what I do always is okay, so we're going to do with our highlighter method again, and I'm going to highlight the vertical transformation. So vertical transformations up here, if you remember, out front and at the end. And horizontal transformations occur inside with the X, and they're like work opposite of what you think. Okay, so we're going to color code like that again. So if I'm looking at this one, this is a vertical transformation. It's out front here. And this plus 60 degrees would be a horizontal transformation. And then I would write out what they are. So this 2 is a vertical stretch by a factor of 2. Okay, so that means I'm going to be multiplying my y values by 2. And then this plus 60 is going to be a horizontal shift, but specifically the plus means left, 60 degrees, but then because we're dealing with 60 degrees, I always like to write the number of squares that it is because I find it really helps me. So it's going to be 2 squares. Okay, so now those are my only 2 transformations, so I'm going to apply them one at a time to my 5 important points. So starting with 0, 0, the y value is 0. If I multiply it, so remember again, I'm doubling my distance from the central axis. So doubling 0, you're still at 0. Then I'm going to shift left 2 squares. So there's the image of this first point here. Here, vertical stretch by a factor of 2, so I'm doubling my distance from the central axis to make it 2, and then I'm shifting left 2 squares. So there's going to be the image of my second point. Third one, doubling my distance from the central axis, so I'm still at 0, and then left 2. for here, doubling my distance from the central axis, so instead of -1, I'm going to be at -2, and then left 2. And then my fifth important point, doubling my distance from the central axis, so still at 0, and then left 2. So I can see these 3 points are going to form a frown. And then these 3, 1, 2, 3 are going to form my smile. And there I've drawn 1 cycle. Okay, but it asks me for 2 cycles of the image function. Okay, so then I should be able to see a pattern. So my pattern is to get from this point to this point, I go over 1, 2, 3, and up 4. And then to get from this point to this point, over 1, 2, 3, and down 4. And then from this one to this one, 1, 2, 3, down 4 again. And then from this one to my last one, over 1, 2, 3, up 4. And we know that it's a cyclical repeating pattern. So I should be able to go up over 1, 2, 3, up 1, 2, 3, 4, just following the pattern. Over 1, 2, 3, down 4. Over 1, 2, 3, down 4 again. But I've run out of room to go over 3 and up 4 to finish it off. I just needed 1 more square and I could have done it. Because this, if you can see, I've got 1 cycle is a smile, a frown, sorry, and then a smile. So here I've got my frown, but I only have half a smile. But what I can do is I can continue in this direction what I would do. So I would go backwards to 1, 2, 3, and down 4. So I have a half smile and another half smile, which makes a full smile, which makes me have 2 complete cycles. Okay, so now I've drawn 2 complete cycles of y equals 2, so I'll just underline that in pencil, y equals 2 sine of x plus 60 degrees. Okay, so I've done the big part of the question. Now I have to do the amplitude. So the amplitude, again, if you remember, is the distance from the central axis, which is still at 0, to the maximum. So this time it's 2. So my amplitude, I don't know if you guys can see everything here, but I'll try to fit what I can. So the amplitude is 2. So amplitude's crossed off. Period. How long does it take for 1 cycle? So if we want to think of 1 cycle, I like to do maximum to maximum because it's just really easy for me to count like that. So maximum to maximum is always going to be 1 cycle. So I'm going to count the number of squares here. Watch me. So here's a maximum. There's my next maximum. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 squares. So my period is going to be 12 squares, but each square is worth 30 degrees. And 12 times 30 degrees is 360 degrees. So the period is 360 degrees. So now I've done period as well. Phase shift. So normally cos starts at 0 and heads upwards. So starts at 0 and heads upwards. So we want to know the closest place to 0, 0, or the closest place to the central axis, that our function starts on the central axis and goes upward. And that's right here. And that is, so our phase shift is left 60 degrees, which is also right in our equation right there. So our phase shift, I use P, instead of writing it out, P dot S. And because it's left, when you write out phase shift, you use negative 60 degrees for phase shift. And it comes right out of the equation. The other thing that's important to note is that the amplitude comes from the equation 2. See how our amplitude was 2, but in our vertical stretch was also 2? So amplitude and vertical stretch are the same thing, okay? And then phase shift you can get from the equation as well as looking right from the graph. I'll talk about how to get period from the equation later, but this is also a very good way to get it, counting the squares for one complete cycle and then multiplying by the scale of the graph. And then domain for what we drew. So let's look here carefully. So domain, we start here and end here. So we're gonna write x is an element of the reals as long as, so the farthest left we go is 30 degrees before negative 180, so that's negative 150, is less than or equal to x, is less than or equal to, and then we go 30 degrees after 540, which is 570. So there's our domain. And our range is lowest to highest, so y is an element of the reals. The lowest we get is -2 is less than or equal to y, which is less than or equal to +2. Okay, so we're using that set builder squeeze notation for the domain and the range, and because the domain, we're just doing the domain for the cycles that we actually drew for the 2 cycles. Okay, so there's our first example of transformation of the parent function sine and cos. Okay, our next question. Y equals cos of 2 bracket x minus 120 degrees bracket minus 2. So again, first step is just putting the scale on the graph. So every third square is 90. Remember to put degrees in. $90 more than 360 is 450. 90 more than 450 is 540. And then backwards, 3 squares, 1, 2, 3, so that's going to be -90 and -180. And then every 2 squares is 1, so up 1, 2, -1, -2, -3, -4. So step 1, just put the scale on the axes, and you're always going to use the same scale. Step 2, draw one cycle of the parent function, y equals cos x, and we're going to use a pencil crayon for that. So we have to erase. And cos is the one that starts at 0, 1, comes down to 0, then down to -1 at 180, back to 0, and finishes at 1. So we have this smile between 90 and 270. And then going into a frown from 270 to 360, and going into a frown from 90 back to 0. So there's our one cycle of y equals cos. So then we're going to look at what we have to draw and identify vertical and horizontal transformations. So here's my vertical transformation, and here's my horizontal transformations that are in the brackets with the x. So then I'm going to write out what they are. So this 2 is a horizontal compression by a factor of 1/2. Minus 120 is a horizontal shift left 120 degrees, and then if each square is worth 30, 120 divided by 30 is 4, so that's 4 squares. Sorry, it's right, my bad here. That's a minus sign, so it's right 120 degrees, which is right 4 squares. And then minus 2, so that's a vertical shift down 2. And then this one's really important. For some reason, everyone remembers to figure out how many squares it is for the horizontal axis, but the vertical axis also has a scale. So going down 2 is really So 2 is really 4 squares, you can see. Okay, and then we're going to use our pencil and transform each one of these 5 parent points for coasts using these 3 transformations. So horizontal compression is going to, in this case, half your distance from the y-axis here. So we're already on it, so we can't half our distance from it. We're staying there. Then we're going to shift right 4 squares, 1, 2, 3, 4, and then down 4 squares, 1, 2, 3, 4. So there is the image of this point. Our second important point, so we want to half our distance from the y-axis, so instead of 90 we'll be at 45, which is like the halfway here. And then from there we're going to shift 4 squares to the right, so 1, 2, 3, 4 in the middle here, and then down 1, 2, 3, 4. So there's the image of our second point. Third important point at 180, so we're going to half our distance from the y-axis, which puts us at 90, and then 4 squares to the right, 1, 2, 3, 4, and 4 squares down, 1, 2, 3, 4. And there's our next important point, 270. So first we're going to half our distance to the y-axis, so that's 135, which is going to be right halfway between 90 and 180. And then move 4 squares to the right, 1, 2, 3, 4, and down 1, 2, 3, 4. And then our last important point, 360, we're going to half our distance to the y-axis, which puts us at 180. And then 4 squares to the right, 1, 2, 3, 4, and 4 squares down, 1, 2, 3, 4. So these are our new 5 points that form one cycle. So we've got our smiley face down here, and then going into a frown. So there's one cycle, and then we should be able to see a pattern that goes from point to point that will get us our second cycle. So our pattern is starting here, we go over a square and a half, down 2 squares. Over a square and a half, down 2 squares. Over a square and a half, up 2 squares. Over a square and a half, up 2 squares. So over a square and a half, down 2 squares. Over a square and a half, down 2 squares. Over a square and a half, up 2 squares. Over a square and a half, up 2 squares. So this time it fits to just go 2 cycles in a row without having to backtrack at all. Though you could have, it's up to you as long as you draw 2 complete cycles. So maximum to maximum and maximum to maximum is fine to make sure that you've got your 2 complete cycles drawn in. And now we have to answer the other question. So we were asked to state the amplitude. So our central axis is no longer the x-axis. The central axis has moved here. Okay, we did talk about the vertical displacement being where our new central axis was located. So if this is our new central axis, the distance from the central axis to a maximum is only 1. So our amplitude, AMP, is 1. Okay? And you can see that the number out in front of the coast is just a 1. So again, remember you can get your amplitude from the equation. Our period, so let's count the squares from maximum to maximum. So I could do that, it doesn't matter which ones I choose, but 1, 2, 3, 4, 5, 6. Okay, so the period is going to be 6 squares times each square is worth 30 degrees, which is 180 degrees. Okay, but I also told you that there was a way to tell from the equation what the period was, and that's using a special formula that the period is equal to 360 degrees, which is the regular period, divided by the B value. And what's the B value? The B value is the vertical compression or stretch. So in our case, we have a vertical, sorry, not vertical, my bad, horizontal. The B value is the horizontal compression or stretch. Okay, so in our case, we have a horizontal compression by a factor of half. but you'll see that we're cutting the period in half because we're doing 360 divided by the b value, and the b value is a 2, which does in fact give us that 180 that we got by counting the squares. Okay, so we could do 360 divided by 2, and that would mean that our period should end up being 180. And then our phase shift. So our phase shift, again, we said we could get right from the equation, so it should be right 120, which is considered to be positive 120 degrees. But you can also see that instead of starting on the y-axis, we're starting 1, 2, 3, 4 squares away from the y-axis, which is 120 degrees to the right as well. Okay. Okay, so we did amplitude, period, phase shift. Now we have to do domain and range. So our domain is going to be the real numbers x, and then we started 30 degrees to the right of 90, so 120 degrees is less than or equal to x, and then we ended, here's 450, 30 degrees more than 450, so that's 480. And our range, lowest to highest, so coming down, the lowest we ever get is -3, is less than or equal to y, and the highest we get on our image is -1. All right, on to C. So y equals 2 sine 3x. We want to draw 2 cycles of it. Amplitude, period, phase shift, domain, and range. But first things first, we'll put our scales on. So every 3 squares is 90. And you can use your calculator if you can't do them in your head, but add 90 to 360 and you get 450, then 540, 630, -90, -180, and then 2 squares is 1 here, -1, oops, and -2. Okay, so first step is the scale. Second step is to draw 1 cycle of the parent. So our parent for this is y equals sine x. Sine starts at 0, 0, then 90 up at 1, back to 0 at 180, down to -1, back to 0 at 360. And it's got a frown, a nice smooth frown, and then a nice smooth smile. So there's our 1 cycle of sine. Then I've got a vertical transformation out front, a vertical stretch, and then a horizontal compression. So let me write them out. So I've got a vertical stretch, and vertical is what it looks like, so by a factor of 2. And a horizontal, opposite of what it looks like, so it's a compression by a factor of 1/3. Okay. All right, so starting here, we're going to double our vertical distance from the x-axis and 1/3 our horizontal distance from the y-axis, so we're going to stay at 0, 0. For this one, we want to double our distance from the x-axis and then divide by 3 our distance from the y-axis. So 90 divided by 3 is 30, so I'd be right here. And then this point, so double my distance from the x-axis, so I stay on it, and divide by 3, so 180 divided by 3 is 60, so I'm going to be here. And then double my distance from the x-axis, so down at -2, and then 1/3 my distance from the y-axis, so 270 divided by 3 is 90. And then my last one, double distance from the x-axis, so I stay on it. And then 360 divided by 3 is 120. So here's my 1, 2, 3, 4, 5 points that I transformed from my 5 important points for my parent. And I should be able to get my 1 cycle in. And now I need to draw 2 cycles, so I have to figure out the pattern. So to get from point to point, it's over 1, up 4, over 1, down 4, over 1, down 4, over 1, up 4. So over 1, up 4, over 1, down 4, over 1, down 4, over 1, up 4. Okay, so then we need to do amplitude. So amplitude, here's my central axis is still at 0. Distance from the central axis to the maximum is 2. Period. So maximum to maximum is 1, 2, 3, 4 squares. So the period is 4 times 30 degrees, which is 120. Or using our formula, period is 360 degrees divided by the b value. And our b value is 3, which also gives us 120. Phase shift. So there's no horizontal shift left or right. So our phase shift we write as 0 degrees because we didn't move left or right. Domain, all real numbers. So we started at 0 and ended at 30 degrees before 270, which is 240 degrees. And our range, lowest to highest. So the lowest we get is -2, and the highest we get is +2. Okay, so that's going to be part 1, and then I'll start part 2 in a minute.